I'll get started while you're doing that. Yeah, I wanted to first ask if there are questions about anything. Today, I hope to finish up on our work on the diffraction of light, or waves in general. There are some interesting things. I don't know that we'll be able to go into depth onto most of them, or all of them, but one that we illustrated early on was the demo that we did, where we had, if you'll recall, we had these styrofoam slabs in which there were holes in a regular array, sort of square array, and in the holes we buried little metal balls in order to simulate a crystal of atoms in a regular array. And the experiment that we did was to have a microwave source. How are we doing?
Both up.
Great, thank you, sir. We had a microwave source which radiated a wave of approximately 3 centimeter wavelength, microwaves, at this box. Well, there's a whole set of them, right? Whose separation was of the same order of magnitude as this wavelength, maybe a little bit bigger. So this is, and what we found was that when we had a detector over here, as we swung this around, there were places where the reflection was large, and we got a loud sound, and there were places where the reflection of this radiation was weak, and we got a very soft or no sound. So there was a pattern with angle of the amplitude of the reflection which went through sort of peaks like this as a function of angle with respect to that series of boxes. You recall that experiment? Well, we did. I think I did that on Monday. It was this is a simulation of crystallography, very important field of research to which a lot of attention is given. We have here at the Lawrence Lab an accelerator which accelerates electrons around a large circle, the circle being probably as big around as including the campanile. If you were to draw a circle around it, it's in a giant room. In fact, the building that symbolizes the Lawrence Lab, there's a symbol of the Lawrence Lab with this dome-shaped thing. I don't know if you've seen it on buses and so on. This accelerator sits inside that building. I think they call it the ALS, the Advanced Light Source. And light by light, what they really mean, it's X-rays. Because as you know, as electric charge, these are electrons actually being sent around almost at the speed of light, just below the speed of light, like 99997 or something of the speed of light, 0.99. We learned that electromagnetic radiation is generated when you have electric charges accelerating, right? If you shake an electric charge, it emits radiation. A steadily moving electric charge does not. That's, again, a relativity effect, you might think, because if I'm in the same frame of reference as a charge, then to respect to me, it's stationary. And all that a stationary charge does is send out its usual, let's say it's an electron. Well, it has an electric field, but it's no radiation. There's no waves coming out of that charge. On the other hand, this is a very important idea. If the charges are accelerating, they radiate electromagnetic radiation at the frequency that they are oscillating. So they send out this field that's they're creating is bobbing up and down, and you get a wave traveling out at the speed of light. So this machine here, you see the charges are accelerating because they're coming, well, looked at it edgewise, they're going around like this, so they're going back and forth. And so they're radiating electromagnetic radiation, and they're going around at a speed such that the radiation that they radiate are X-rays. And the beams of X-rays come out, and people put samples like this over here to try to understand the structure of these materials. So, and that's a very, very expensive machine dedicated just to generating X-rays for the purpose of crystallography. And the reason it's advanced is because the beam intensity, the strength of the X-rays that comes out is very good and is very large. The brightness, they use the word brightness. And the point being that the brighter the light is, the more quickly you can get the answer, right? I mean, it makes sense. If you had a weak beam, you get a sort of weak diffraction. You know, it takes a long time. Here you can get the answer pretty fast. And you can also see weak reflections that you might not be able to see with an ordinary X-ray machine. So the point is that this is a very important technique, as you well know. But so I just wanted to very quickly go over the... we won't have any music today. I was going to play at some suggestion... because I'm going to be talking also about the resolution that telescopes give. We'll again mention Galileo and his telescope. And the fact that he first saw Jupiter with his telescope and the moons of Jupiter. He was the first to see that. So I was going to play the Jupiter Symphony of Mozart, but I don't have time for that right now. I'm going to listen to it later, maybe. But I wanted to go back to... here we go. Well, let's see. I thought I passed it. No. Oh, here it is. Okay. This was the demo that we did. And the very simple argument that is used to determine at what angle would these bright reflections occur if you had a certain wavelength of light that you're sending in, or X-rays, into a periodic structure like this. So the story is that you just imagine that these atoms form a plane. Now, in fact, they can form various kinds of planes. A simple cubic structure like this, you can imagine the atoms being in a plane like this and a plane like this. But you could also draw planes like this. You see, so you can get scattering off various different things, various different planes, depending on how you draw the planes. But let's do a simple case, namely have the waves coming in at some angle, and the point being that the idea of getting a maximum is when the path difference between two waves would be a full wavelength, so that you get a maximum when delta R is equal to, well, so m lambdas. In other words, if you have a full wavelength, then the waves, as we said, will come back in step. So the idea is that if you have a beam of radiation coming in to this structure, the idea is that you want to find out how much larger length, path length, does this part of the beam have than this part of the beam. So what you do is you draw a perpendicular here and say, well, up to here they're the same. Then this fellow will reflect. Now, there's a funny thing. The crystallographers take the angle here for some reason. Up till now, we've been taking it with respect to the normal. The crystallographers somehow grew up in a different scheme, and you'll see in the picture in your book and also on my PowerPoint here that they take the angle theta here for some reason of historical choice. I don't know why. So that angle is let's see. This would be 90 degrees, and if that's theta, this is the complement of theta, and so this is the complement of this is theta in here. Okay, and if this is the spacing between the planes, that's the hypotenuse. So this length here is an extra path length. And then this wave reflects in some direction, and again, you see from here on out, this is the key idea. Up till here, the waves have the same path length. This beam reflects and has that total path. This one goes a little further, reflects, and then from here on out, they're the same. So the question is, how much larger is this part? And this part here, delta R, is d sine theta, but there are two of them, so that the total of delta R is between the difference that this beam goes compared to that beam is 2d sine theta. And when that delta R is m lambda, is a whole number of wavelengths, you'll get a peak, a maximum reflection. This idea here. And so, knowing the wavelength of the radiation, and if you measure the angle of the strong reflection, you can get that d, the spacing of the crystal, is m lambda over 2 times the sine of the angle of this particular angle. So that's the basic theory of X-ray diffraction. And it's good to know. Some of you may in your life actually do that kind of work. So that's one. Now, just for fun, let's break things down a little bit here. I wanted to get you to have an experience seeing a diffraction pattern. So why don't we have here diffraction gratings, I'm told. Warning, do not look directly at the sun. That's a good idea. Why don't you come, well, I'll tell you what, let me pass these around. Maybe you can see them even from your seats. Would you help me pass these around? And what I'll do is do give them back to me at the end. You want to pass them around a little bit? Now, to make things a little bit brighter, I can turn down the lights a little bit. The idea is I'm going to turn on lamps that have specific chemical elements in them. Mercury. Mercury is blue and violet, it tends to be. Maybe I should get out in front and see what it looks like, actually. Now, if you look at this, and off to the side, you will see sort of hopefully bright lines. Maybe I should try one myself here. Maybe I have to turn on more lights. Yeah, off to the side. You see, what's happening is the light is coming off to the side and is diffracting off to the side to you. And you're seeing the individual colors of that mercury emission. Now, let me turn that one off, and let's try, this is neon, this should be red. Yeah, there's a whole band of lights there, huh? Different colors. So that's the characteristic color when you excite the electrons of neon. You see it off to the side? You can see them off to the left and to the right, I think. Those are all individual lines of the argon, neon. Now, what's this guy here? I don't know. Let's try it. Sounds like something out of a science fiction movie. So what this grading is doing, I don't know how many lines there are. Does it say? Can you see the different colors, different lines? All right. Well, this has a twofold purpose. First, I wanted to demonstrate for you, and you can hang on to the gratings and come up later and play with this if you like. But do return them at the end. There's two purposes here. First, to illustrate the idea of a diffraction grating, which we have seen is the point being that in a diffraction grating, what you have is many, many slits rule gratings, and they're close enough together such that when a light of a given wavelength or frequency arrives here, you get n lambda is d sine theta m. Let's call it m. I think I called it n before, but it varies. Just an integer. When you get this kind of thing, you get these bright fringes. And so what this is doing is spreading out that light that's coming from there into its individual wavelengths. And that's very powerful. If you know the grading, now we turn it around. Usually with something like this, we know the spacing. We know D because we make it. We make D certain amount by some mechanical process. We make slits. And once you know D, and if you know the angle through which you're looking, you get lambda from lambda is equal to d sine theta over the order of the refraction. That is how many wavelengths you have. So this is a spectroscopy thing where you're trying to determine the wavelength of the light or the wave. Or if you know the wavelength, like in the case of the X-ray, you know the wavelength, you can get the spacing. Now, what you can do is you can combine them. You can use a grating to get a particular wavelength and then shine that wavelength on something else and get a spacing. You see, because it's a way of filtering the light, sorting out the different wavelengths. So there's wonderful combinations that you can make out of this. Now, a very useful idea. Well, now the book also goes into thin film interference, and here is another way in which one can make two beams of the same wavelength and frequency overlap each other and hence produce an interference effect. And that is you reflect light off the top surface of a film and then off the bottom surface. And so the two beams have undergone different paths, lengths, and if they come in out of step, they interfere. If they come in constructively, you get a bright fringe. And you can get this effect. For example, you sometimes see an oil slick and it'll have colors because the waves of the certain color are constructively interfering. The tricky part here is that you have to figure out the phase shifts here. The phase shifts for several reasons. One, because the light is traveling through a longer distance is one thing. The other thing is traveling through a different medium. And so its speed changes. And so its wavelength changes. So you have to count the number of wavelengths that it's traveled before it recombines with the initial wave. And the third thing that happens is that there is a phase shift when you reflect off a medium of higher index of refraction. So you have to take all of those phase shifts into account, and that is explained in the book, and I don't know that I have to belabor it here. The other thing that I did point out to you, that you can get diffraction from a single hole, slit or circular hole, and parts of the light coming through the slit will interfere with other parts of the light coming through the slit. So you can get diffraction effects through a single slit. And you get bright and dark fringes, and we actually did a demo of that last time. Now, the formula there, well, I don't want to belabor it. Now, there is something that you will be using in next week's lab. It's the idea that, and I don't know that it is even explained in the book, but I think you'll be doing something like this. You'll be asked to take a wire, and light will a laser will pass over the wire, and you will see bright and dark fringes in the shadow of that wire. And you'll be asked to sort of analyze the situation. So this is an opaque wire. Now, the thing that you have to know is that the diffraction pattern of the wire is the same as the diffraction pattern of a slit. This is not immediately obvious. So if you have a slit of the same dimension, let's say that is a wire of width, let's call it A. If you have a slit of dimension A, it produces the same diffraction pattern. That's not terribly obvious. But again, a clever Frenchman by the name of Babinet, which sounds like cabinet, the cabinet, but it's Babinet. He proved very cleverly, and I have the proof here on the next slide. It's in my PowerPoints. Why, if you have, you're going to start out actually with the case here, with a opaque barrier, and you're going to be asked to talk about the diffraction to a place way up here. The idea is that we haven't really given you a formula for how do you count the diffraction at a point outside a wire, but we have told you how a slit behaves. And how a single slit will produce a minimum over here. Well, the point is that the sum of the light passing through here plus the sum of the light passing through here is the same as this, so that these two together should add up to this. And before we put these obstacles here, there was no light here. It was just a laser beam, so that the light produced by this setup should equal the light produced by that, except in opposite phase. That's the theory behind this Babinet's principle. So, but since the phase really doesn't matter as far as the brightness goes, because you square the electric field to get the brightness, you will have a bright fringe here, whether you have it coming through a slit or whether you have it diffracted off an opaque barrier. So you'll be using that next week, I think. You haven't done that yet, right? As I understand, it's next week. Okay. So I just point that out to you now because it's not in the book, and I really don't know why it's in the lab experiment, but here you go. Here's the explanation of why it's okay, so that if you need a formula for the scattering off of a small object, it's the same as the scattering through a small slit. You'll get the same diffraction pattern. Okay, that's good to know. And you will be confronted with it next week. And here, again, I talk about the fact that you have, with a diffraction grating, you have two things going on. You have the light that passes through the many slits, which produces this kind of a pattern, and you have the light that passes through one slit, produces this pattern, and the net effect is a pattern that looks like this, which is what you see here. You get the many lines are produced by the many lines in the grating, but it's modulated by a bright spot in the middle, which is a single slit pattern, be that as it may. Okay, now I've shown you this. You have the gratings in your hand. The other thing we want to talk about quickly is something that should not surprise you at this point, and that is that if you have, instead of a single slit, you have a circular hole. What is the diffraction of that? Well, you can think of a circular hole as a slit that sort of closes on itself, if you will. Because we had that if you had a slit and the light's coming in, and we have the Huygens principle where the waves will be going out from every point on the wave front, and you get a minimum. Again, we're using the same trick. Namely, if I have a screen over here, if I draw an arc, the wave from along these arcs, from here on out, the two waves are the same, have the same path length, right? From here or from here. The difference in their path length is the distance from here to here. Here's your the difference in path length. And so if this is a half wavelength, then by the time they have the same path, they are out of step by a half wavelength. So you get a minimum over here, or a dark spot, when this is the whole aperture here, whole being spelled both ways. It's the whole aperture and the whole aperture. It's A over 2 sine theta is the extra path. A over 2 sine theta is the extra path length to give you the waves half wavelength out of step, and from there on out, you see, they are the same. You get that picture? It's the same story over and over again. You just have to find when they're the same along this arc, and if it's close enough, the curvature of the arc won't matter if that's far enough away, so we can say that what you're dealing with is a right triangle here with an angle theta at that angle here. The extra path length is A sine theta. That's the extra path length. And so the formula for the minimum or destructive interference is the 2's cancel. Lambda is A sine theta. For a minimum. And so knowing one or the other, you can find whatever you need to know. If you measure the angle to the minimum, okay, so that's what you get. Now, so that's for a slit. But if you have a circle, what you might think of is the slit being sort of closed down around it, like that. So previously it was like that. Well, now I'm closing it all over. And the formula changes just a little bit. For the case like this, you get, 1.2, d sine theta. Lambda is 1.2 A sine theta. I think that's about what it amounts to. No, whereas the 1.2 is on the other side. Huh? It's such a small factor, it doesn't really concern us too much. So it's what I would think is what it means is that the D is a little bit smaller than it should be. In other words, what I would do here, instead of having A, I would say that A is smaller. So I'd say, let's say A is over 1.2 sine theta is lambda. You see, because previously the slit width was A. Because I'm closing it down, I'm kind of making the slit smaller. So maybe that's a better way to look at it. So you have 1.2 lambda is equal to A sine theta for and that comes out. Yeah, that comes out what a fancy calculation would give. So that's one way of looking at it, namely that the hole is just a slit that's sort of closed up a little bit. Now, why this is interesting is that you can think of anything being made up of small spherical bits or pixels, if you want. And so you can ask questions like, one question that's interesting is, how close to two spots will they look separate? Which is known as resolution, or when are the spots resolve? In other words, one of my favorite examples is in art. You may have seen this picture before. It's a famous picture by a French artist, Seurat, and he painted this. This is one of a very famous painting, and his style of painting was that he had the theory that instead of putting paint down on a canvas and mixing the paint on the canvas in a palette and putting it down to try to get a color, he said, let me start with pure color and just put the pure color down, but I'll put down such small dots that when you're far away, your eye alone will merge the dots. And so you will see, the color should be, he thought, more vibrant. So this is the kind of style of painting called pointillism, points of paint. And so we have here let's see, above the dog, right in here, that little area, this is what it looks like on expansion. And if you expand it even more, you see that he's just put down little blobs of paint. Boop, boop, boop. This must be a very tedious process. I mean, how many dabs of paint he must have put into this whole picture. It's a big picture, by the way. It's really quite a lot of time. Let me go back. And the idea is that if you get up close, again, if you go up close, you see the dots. But if you stand far enough away, it looks like smooth paint. You know, it's a theory. I think there was one other fellow who followed him in this pointillist style. This is the years of the Impressionists, about 1900, 1910. And so we can do the physics of that, as you were afraid they might. And that is to say, if you have a dab of paint, let's say 2 millimeters, and the pupil of your eye is roughly, let's say 1.5 millimeters, how far do you have to go so that the dots will look merged? Now, the criterion that's used is that if you have a dot and another dot, you see, again, this could be thought of as by the Babinets principle, this could be an aperture, and the aperture has a bright spot, and it has a dark ring. The first dark ring is given by 1.2 lambda over A is a sine of theta. But if you're far away in radians, that's approximately equal to theta. So the idea is if you have the two dots and the light is coming out of here, passing through the pupil of your eye, which is, let's say for the sake of argument, 2 millimeters. I don't want to be too fancy here. That dot will produce an image, because of the diffraction of the hole, it produces an image that looks something like this, with a dark spot at an angle given by the width of the eye here, the diameter of the eye, and the wavelength of the light. And so you'll get an angle here. Now, the question is, how far away can this be when that angle gets when you subtend a smaller angle, the further away you get, the angle gets smaller and smaller. And when you're below that angle, the two dots look merged. I think I actually have a... so this explains that. In other words, you have to be at a distance greater than 6 meters when all the colors, including the blue, get merged, and the two dots that close enough together, at say separated by 2 millimeters, seem merged in your eye. There'll be one color. I have this other interesting demo here, where you see if you have a single source, it creates a diffraction pattern that looks something like this with its first minimum here. The criterion, now suppose I bring these two guys close together, if I can. Separation. If I bring them close together, the criterion is that when the peak of this is in the minimum of this, then we would say that the two are one big blob. So I'm trying to bring the peak of this, it's more or less right. See, it's pretty hard to tell that there are two blobs there. You know, I pull them apart, and you see, these are the separate patterns of each of the sources, called Airy, another Frenchman. But when the peak of one of the blobs is in the minimum of the other, it's called the Rayleigh criterion. And we would say that the two blobs look like one as far as we could tell. You really can't say that there were two blobs there. And this is interesting from the point of view of astronomers who are trying to do that. For example, if they want to know whether there are two stars there or one, they have to they have to get the resolution the angular separation of these greater than this Rayleigh criterion. Now, one way of doing that actually is by changing the wavelength of the light, because the angle at which you can resolve these gets greater if the wavelength gets shorter. You can actually see them separate more. Like, for example, if I go to here, see, it sort of pulls them apart, whereas if I go to more red, they get more and more merged, because the longer wavelengths spread more. The shorter wavelengths are a little bit narrower peaks, and you don't quite reach the Rayleigh criterion. This idea has some rather important manifestations, actually. The idea of when you resolve things. Let me load this back up again. Okay, so you can go through this and see that as you get further away, the angle that those two dots are separated by gets less and less, and finally it gets lower than the Rayleigh criterion, and by that means a red dot and a blue dot of paint would be merged together, and you could get some intermediate color. So that's the pointillist idea. The other concept, though, is that this, as I mentioned, it's very important in astronomy, because the astronomers want to know whether there are two stars out there, or whether when you see a blob, whether it's really a galaxy or one great mass of gas. Are there individual stars, or are there just a vague collection of gas. So the resolution of the eye, for example, if you, I don't have time to go into this. This particular slide comes from the Hubble telescope, a website, where they point out that at the human eye was able to see objects a certain angle apart. You can judge by the angle. When Galileo made his telescope, it improved things 20-fold. That is, you could see even a smaller angle. What you want to be able to do is see things that are smaller and smaller, closer and closer together, subtending a smaller and smaller angle. Now, the reason he did that is because what you're doing is you're replacing the human eye, which has a pupil, an opening, as we said, about 2 millimeters. Galileo replaced it with a telescope with a lens about that big, so the diffraction pattern was, because the A became much bigger, the angle through which he could see gets to be much less by this factor of the size of your pupil to the size of the lens, which was from 2 millimeters to about, say, 5 centimeters. So there's your factor about 60 or 30 or so. What is it? Yeah, about 20. Well, is it 20, huh? 20 times better. It's the ratio of the pupil of the eye. Now, when they built the Mount Palomar telescope, it's a 200-inch telescope down in Palomar, and I think it's near Pasadena. It's the world's largest reflecting telescope, glass telescope. Now, 200 inches is, turns out, 5 meters. So you would think that that would be a lot better, but it turns out that it isn't that much better. It's only 3 times better than Galileo. The reason being that it's not the diffraction, it's not the spot size that's affecting the Palomar telescope. It's the scattering of the light in the air. Turbulence in the air kills the image. So they actually put up the Hubble telescope, which is a smaller mirror than the Hubble telescope is only 2.5 meters. It's about half the size of the Hubble, but because it doesn't have the turbulence of the air, it's really limited by diffraction. And so you get the full improvement from 5 centimeters to sort of 5 meters, or 2 meters. The Hubble is 2 meters. So you gain that you can see things that are very, very angularly separated. So that's one thing. The other thing is this, namely, not only do you want to see things that are large, but you want to make things that are small. And so one of the things that goes into your cell phones and computers is they try to make things as small as possible, these little circuit elements. And one way of doing it is by making a mask and shining light through the mask onto a polymer, which changes by photochemistry the nature of the chemical here. And so you can sort of maybe wash that chemical away and then embed ions and stuff like that in here, make a circuit in here. But the question is, how small a spot can you make? And because the light is diffracting out, the spot size can get too large. So they go through all kinds of gyrations to make smaller and smaller spots. Small is beautiful was that they think is good at IBM, but small is beautiful. So they would make things as small as possible, and it turns out that what you want is the shortest wavelength as possible to make steep walls without spreading of the light beams. So what you have to do there is go to shorter and shorter wavelengths, blue light, and even IBM built themselves one of these electron accelerators in order to get X-rays, in order to make circuits. So that we then end up with circuits like this with extremely sharp walls, and then you can lay down chemicals in here. And then you've heard of Blu-ray, thank you. The Blu-ray and high-density CDs. What they use is blue light rather than red light because they can make the spots in the recordings closer together and pack more information on this. It turns out that the people who invented the blue laser won the Nobel Prize last year for inventing a blue light, which has two features. One, you can make things smaller, and also you can mix red, green, and this blue and make white light. So this is a huge step forward, and that's won them the Nobel Prize. The other thing I wanted to tell you about was the scattering of light. And again, this is an effect. The fluctuations in the air scatter light, depending on the length. Again, it's a length effect. You want the wavelength, so sort of the size of the thing that's scattering, to give a big scattering effect. So it's easier to make a short fluctuation in the air than a large one. So what happens in the air is that there are small fluctuations of the air density just by statistics, and that scatters the short wavelength light stronger because the wavelength is more matched to the size of the fluctuation in the air. Look, air is a gas. The molecules are flying around. Sometimes they're a little more packed, sometimes they're a little less packed. If you get but it's easier to make a small fluctuation than a big fluctuation, right? So small fluctuations happen more often, so small wavelengths are scattered more. That's why, for example, if you stand here in the middle of the day, you'll see blue light coming down. So the sky looks blue. But if you go at the end of the day, all the blue light has been scattered out, and the sunset looks red. So that explains the red sunsets. And if you fly in a